There are many questions to ask yourself when designing a coil gun, from how many turns or layers of wire the coil should have, what diameter of wire to use, and the numerous other factors that play a role in determining the strength of the magnetic field. In this video, we'll be exploring these ideas, why they have the effects they do, and how changing various circuit design parameters and the projectile material affects the performance. We'll work our way through these by looking at the electrical current flow through the coils by simulating the system and seeing what is happening through the process of firing a projectile. The first principle that comes to mind when thinking about an electromagnet is the magnetomotive force, which is the flux-producing ability of an electric current in a magnetic circuit. The equation that describes it is magnetomotive force equals I by N, with I being the current flowing through the coil in amps multiplied by N, the number of turns in the coil. Therefore, to maximize the magnetomotive force, we need to increase either the current or the number of turns. But they do come at the expense of one another, as when we increase the number of turns in the coil, the resistance then also increases, which leads to a lower current, or the inverse of that is decreasing the resistance through having less turns to allow a greater current to flow. But is this really the whole picture? As changing the number of turns affects the inductance of the coils. So why is this important? And how does it impact the performance of the coil? To start with, an inductor wants to remain at a steady state and will resist any change in current by generating an EMF to achieve this. When the current is increasing and the magnetic field grows, the EMF is induced in the opposite direction of the applied voltage, which slows down the rate at which the current can increase. Then, when the magnetic field collapses, the EMF is induced in the same direction as the original flow in an attempt to maintain that current. A good analogy to explain what is happening is comparing the equation for the voltage across an inductor to the equation for force. Where the voltage across the inductor is analogous with the force, the inductance with the mass, and then change in current over time with the change in velocity over time, also known as acceleration. In this way, you can visualize how having a larger mass, in this case the inductance, means the acceleration or change in current will be lower when the same force or voltage is applied. We can test this by comparing different coil constructions to a baseline. To keep these experiments consistent, we'll be using the same capacitor bank charged to 400 volts. Although the variables, such as the time the coil is energized for and the distance the projectile is placed from the center of the coil, will be set independently to achieve the best result for each coil design. The reason these variables are critical is that in the case of the coil's energization time, we want the power to be switched off once the projectile reaches the center of the coil. This is due to the same magnetic force that accelerated the projectile at the start will now, if there is still current flowing in the coil, begin to slow it down as it passes the center and exits through the other side. The distance the projectile is placed from the center can affect its final velocity, as if it's placed too close to the center, the projectile won't have time to accelerate to a maximum velocity before the center is reached and the power is switched off. When it's placed too far from the center, the magnetic field strength out at that distance is too small to apply any significant force to the projectile. And by the time the projectile reaches the center, where the magnetic field is the strongest, the current flow will be at a minimum as the capacitor bank will be significantly discharged by that point. To see the real-world effects of this, we'll compare the projectile velocity and energy of 3 different coils to a baseline. 2 of the test coils will have the same wire diameter, but one will be wound with one less layer than the baseline, allowing a higher current flow but at the expense of fewer turns, and the other with one more layer, increasing the number of turns but at the expense of a lower current. The last one will have the same number of turns and layers as the baseline, but will be wound with a thicker 1mm diameter wire, allowing a higher current flow with the same number of turns. To set the baseline, we'll be using a coil wound with 0.8mm diameter wire in an arrangement of 6 layers of 70 turns with a mild steel projectile, 10mm in diameter and 30mm long. To start with, the baseline reached a velocity of 25.4 meters a second, giving it 5.49 joules of kinetic energy. With the additional layer on the coil, it decreased the velocity by 3.5% to 24.5 meters a second. But it did have a higher efficiency at 3.55% compared to the baseline's 3.16%, due to the less energy from the capacitor bank being used. When the coil had one less layer, it achieved a 1.2% increase in velocity to 25.7 meters a second. So it looks as though, in these cases, the magnetomotive force is influenced more by the increase in current than it is negatively affected by the reduction in the number of turns. Now to the coil with the same number of layers and turns, but with the wire diameter increased to 1 millimeter. We would assume an increase in velocity as we are increasing the current while keeping the same number of turns. With this arrangement, we measured the velocity at 26.5 meters a second, which is an increase of 4.3% and was in line with our initial assumption. After collecting these results, this now gives us the values and information required to build a model of each system so we can see how the current and therefore magnetomotive force changes throughout the firing period of the different coil setups. To start with, we need to create a function for how the inductance of the coil changes depending on the position of the projectile. Our initial inductance is measured by placing the projectile at the same distance from the center that we set it to during the test. Then, measuring it again when it's at the center of the coil. A function and circuit can then be produced that simulates the inductance change between these 2 points over the time the projectile takes to travel between them. Adding this function into the circuit with the rest of the system and simulating it, we get a plot of the current through each coil throughout the firing period, which when then multiplied by the number of turns in each coil, gives the magnetomotive force produced. Looking at the plots and comparing them to the test results, as we would expect, the coils with the higher velocities also had the higher magnetomotive force. The coil wound with the 1 millimeter wire produced the greatest force, followed by the coil with one less layer than the baseline coil, and finally the coil wound with the additional layer. One thing that does draw my attention though, which you may have picked up on too, is at the point you switch the power off, there is, although decreasing, still a current flowing through the coil, which means there is still a magnetic field present slowing the projectile down as it exits the coil. Later in the video, we will look at how to significantly improve the performance by decreasing this recirculating current and its magnetic field. While testing the previous coils in regards to the magnetomotive force, there were changes to other factors of the coils that weren't taken into account. In particular, its dimensions being the radius and length. If we look at how the change in coil length affects its performance, it leads us to the magnetic field strength, which is the measure of the intensity of a magnetic field within a given area and is measured in ampere turns per meter. Looking at the equation for magnetic field strength, H being the magnetizing force, I and N, as we have seen earlier, being current and number of turns, and finally with L being the coil's length in meters. With the addition of length being taken into consideration, we can see as previously, the higher the current or number of turns, we get a higher magnetic field strength, but with length being in the denominator, the larger it becomes or the longer the coil gets, the lower the magnetic field strength becomes. So what role does the coil's radius play in all this? Besides increasing or decreasing the resistance depending on the number of layers wound, it plays a role in determining the inductance of the coil. The inductance is determined by the multiplication of the permeability of a vacuum, the relative permeability of the core, the number of turns squared, pi, and the radius of the coil squared, all divided by the coil's length. Here we can see, as we increase the radius of the coil, its inductance will also increase. When the radius is increased by adding additional layers, we can see the significant effect it has on the inductance by increasing it by both the square of the number of turns and radius. Although having a higher inductance, as we have seen, can lead to a slower increase in current, this change in current is also dependent on the resistance of the coil. How quickly the current builds in an inductor is determined by the inductor's time constant, which is the ratio of the coil's inductance to its resistance, known as its L/R ratio. We can see how increasing inductance against a fixed resistance or decreasing the resistance against a fixed inductance increases the time constant, meaning it takes longer for an inductor to reach its steady state current, compared to having a higher resistance to a lower inductance, which decreases the time constant, so it reaches its steady state in a shorter period of time. But we can't just design our coils around increasing the resistance to try and offset a high inductance, as our maximum current in that case will also decrease, leading to a lower magnetic field strength. To test these effects, we will start with a coil wound with the same wire as the baseline and keep the same number of turns, but shorten the length by moving the turns on the end of the coil to an additional layer. Will this shortening of the coil length overcome the decrease in current due to more wire being used to wind the turns on a large radius coil? When testing this coil, the decrease in current affected the performance more than shortening the length attempted to improve it, as we measured a velocity of 25 meters a second, which was a decrease of 1.6%. Next, we'll keep the exact same coil radius and length as the baseline, but change the wire diameter to 1 millimeter. This ends up giving us an arrangement of 5 layers by 56 turns. In doing this, we will have a decreased resistance, meaning an increase in maximum current, but less turns to contribute to producing the magnetic field. We also expect to see a reduced inductance due to the fewer turns, allowing a faster current ramp. This coil had its performance improve significantly from the increased current and reduced inductance, where its measured velocity increased by 4.3% to 26.5 meters a second. What if we now increase the radius above the baseline coils, keep the same length, but use the increased 1 millimeter wire, so the coil has 6 layers by 56 turns? In this case, although the radius has increased, the number of turns is fewer, and we end up overall with less inductance. With the length being the same as the baseline, the performance will come down to the current ramping up quicker and there being more of a gain from increased current than there is loss to having fewer turns. It didn't perform as well as the 1 millimeter wire coil with 5 layers and 56 turns, which is expected, but compared to the baseline, had a 3.1% increase in velocity to 26.2 meters a second. Once again, when we simulate each of these designs, we see that the coils with the higher magnetic field strength aligns with the coils that measured the greater velocities during testing. Now we have seen how the inductance and L to R ratio affect a coil's current flow and therefore its output. We can now look at a case where having a higher inductance while keeping the same coil dimensions and resistance may provide a performance gain. This is done through the material choice for the projectile, in particular using a material with a higher permeability. The higher the permeability, the more susceptible the material is to a magnetic field, meaning the magnetic circuit will have a lower reluctance. The reluctance of a magnetic circuit is the equivalent of resistance to an electrical circuit. So in a similar way that resistance restricts the current flow without taking into account factors like heat dissipation, the reluctance opposes the flow of magnetic flux for a given magnetomotive force. So to test this, we will compare a mild steel projectile, which has a permeability of about 2000, with a soft iron projectile that has a permeability of about 5000. When measuring the inductance, we can see it is higher with the soft iron projectile in the center of the coil, meaning there will be a decrease in the rate the current ramps, but will the gain from the higher permeability projectile be able to offset this? This time, we will start backwards and create the models based on the differing inductance measurements of the two different projectiles. With all other factors being equal, we will predict the outcome based on the current waveforms. In this case, the soft iron projectile is slightly lower than the mild steel projectile, which would lead us to believe, going by previous tests, we will have a lower velocity. Though when testing the soft iron projectile, the velocity measured slightly higher at 25.5 meters a second compared to the baseline of mild steel at 25.4. This higher velocity means the projectile also has a higher kinetic energy, which leads to another benefit. Since the soft iron projectile required less energy from the capacitor bank to reach its final velocity, there was also an increase in efficiency too. Taking things one step further from using a projectile with a lower reluctance, what if we lower the reluctance of a larger section of the magnetic circuit? This can be done through an idea that regularly comes up of adding an external shell to the coil. The reluctance of a magnetic circuit is equal to the length of the circuit divided by the permeability of a vacuum multiplied by the permeability of the material and the cross-sectional area of the path. To demonstrate its effect in a simplified example, we can look at an electromagnet's iron core, but with a small section cut out, creating an air gap. To calculate the reluctance of this magnetic circuit, we have to do it in two parts. find the reluctance of the core, and then of the air gap. For the core, we work out its length and cross-sectional area, then we divide its length by the permeability of a vacuum multiplied by the permeability of the material, in this case iron, multiplied by its cross-sectional area in square meters. Now doing the same with the air gap, we have a much smaller section but end up with a reluctance that is a magnitude larger. These two values then added together give the total reluctance for the circuit, and as we can see, the greater the air gap is in a circuit, the higher its reluctance will be, leading to a greater opposition to the magnetic flux. If we measure and compare the inductance of the external shell coil against the baseline, it measures slightly higher at 548 microhenries compared to 515 microhenries. So what are we expecting to happen? Will the lower reluctance of the magnetic circuit make a difference? Or will the slower current ramp due to the increase in inductance mean there's less current overall contributing to building the magnetic field? When testing the coil with the external shell, we measured a slightly lower velocity than the baseline at 25.2 meters a second, which appears the reluctance of the magnetic circuit wasn't decreased like we thought it would, or there are other unknown factors here at play. If we now remember back to the beginning of the video when we looked closer at the current waveforms during the simulations, we saw once the power was switched off, there was still a current flowing through that coil for a period of time. This isn't ideal, as we know whilst there is a current flowing through a coil, there will be a magnetic field present. So if this is happening as the projectile is exiting the coil, there will be force acting on it, pulling it back in. So what is causing this? Well, all the power we have delivered to the coil to build up the magnetic field needs to go somewhere once the power is switched off and the field collapses. In this case, it is converted back to electrical energy and recirculates through the freewheeling diode and coil until it is dissipated. If we want to minimize the effect this recirculating current has on slowing down the projectile, we need a way to dissipate this energy quicker to reduce the unwanted magnetic field. The way to do this is by using this excess power by putting it through a load, which in this case will be done by adding a resistor in series with the freewheeling diode. To see if we will get the desired outcome, we can simulate the coilgun circuit with the addition of this resistor. When we do, it shows a significant reduction when compared to the baseline, but it does come with an adverse side effect, which can be seen when we probe at the collector of the IGBT, we see a voltage spike. So why does this voltage spike appear? Well, when we look at our coil at the point it is switched off and the magnetic field collapses, it has effectively now become a current source as it wants to maintain that current flow. With the current now needing a new path, it goes back through the freewheeling diode and resistor. So doing a quick back of the napkin calculation using Ohm's law, we know the current at the point we switch the power off, multiplying that by the circuit resistance, we get an approximate value of that voltage spike. This is a bit of an oversimplification for what is happening, but a good starting point. As going back to the inductor voltage equation, the voltage is dependent on the change in current in respect to time. So the faster the current changes, the higher the voltage across the inductor will be for a given inductance. This voltage spike can be lethal to our switch components if it exceeds their voltage rating. So what can we do now to decrease this spike? In this situation, we can add a snubber circuit which consists of a resistor and capacitor placed in parallel across the IGBTs. Its purpose is to dampen any voltage and current spikes along with oscillations. With the addition of the snubber circuit and simulating the system, the peak of the voltage spike is about halved and is now down to a level that the IGBTs can handle. Now to test this idea by using the baseline coil and comparing it with and without the discharge resistor and snubber circuit, there is a clear winner. With the discharge and snubber circuit arrangement, the projectile achieved a velocity of 28.3 meters a second, which was an increase of 11.5% over the baseline's 25.4 meters a second. An interesting find though is that the coil with the snubber and discharge circuit achieved its best result when it was energized for a longer time than the baseline test. So it appears as though in earlier tests when we thought we were switching power off when the projectile reached the center of the coil, that wasn't actually the case. In these scenarios, the optimum time to switch the power off was at a point prior to the projectile reaching the center, where some of the recirculating current was contributing to accelerating the projectile, but also allowed time for that current to taper off before it passed the center, minimizing the force decelerating it. I hope you enjoyed this video and now you have some knowledge to build or improve your own coil gun. If you want to see more videos, subscribe. If you have any questions or other ideas you want to see tested, comment them down below.